Hey everyone, so this is the lesson on the problem walkthrough for the Newton sums. So this is like the problem video, so if you guys haven't already seen the video lesson on Newton sums, I highly recommend that you check that video out before watching this one. So without further ado, let's begin with the first problem here. And so the problem is, suppose x and y are positive integers such that xy plus x plus y is equal to 71, and x squared y plus xy squared is equal to 880. So this is like a common problem type in math competitions where they're going to ask you for like a relationship between a bunch of the variables, and then they ask you to find another relationship between the variables. So a strategy that we can use to solve this problem here is that we can create a polynomial that has these roots. So suppose we have a polynomial p of t is equal to t minus x t minus y. So that means x and y are the roots to this polynomial p of t, right? And so then what we have is we can use Vieta's formulas to relate these two roots. So I'm going to use this notation to denote the elementary symmetric sums. So let S1 be equal to x plus y, and S2 is equal to xy. So then what we have is S1 plus S2 is equal to 71, and this is equal to xy times x plus y. So then this is equal to S1, S2 which is equal to 880. So now we can just solve this manually. So we do a substitution. So S2 is equal to 71 minus S1. So then S1 times 71 minus S1 is equal to 880. So then S1 squared minus 71 S1 plus 880 is equal to 0. So then once you solve this using the quadratic formula, you're going to get that S1 S2 is equal to 55 16 or 1655. So then what you can do is you can use these two values of the symmetric sum to rewrite the polynomial. So then p of t, right, which is equal to x, or t minus x t minus y, is also equal to t squared minus 16t plus 55, or is equal to t squared minus 55t plus 16, right? Because there obviously it's possible for there to be more than one solution. So now what we have to do is we just solve both of these equations to see what we get. So if we were to solve this one first, so this first equation, we get that the solutions are going to be t is equal to 11 and 5. And if we were to solve this one using the quadratic formula, we will find that this one has no solutions, because the discriminant is not a perfect square, which means that the two roots of this equation or of this polynomial will not be integers. They're going to be irrational. So that's why we can rule this one out, because the initial condition states that x and y are positive integers here. So that means that this will have to be the only solution. And so we wanted to find x squared plus y squared, and this is going to be equal to 11 squared plus 5 squared, which is equal to 146. And so that's the only solution. So now I have one more problem here, so I'm just going to write it down first. So okay, find all complex Okay, so basically it states that we were trying to find all of the triplets of solutions x, y, z that satisfy these equations here. So the first thing that we should notice is that these are just the Newton sums of the or the power sums of x, y, and z. And so then what can we immediately do? We can create a polynomial. So let's say we have another polynomial p of t, which is equal to t minus x, t minus y, t minus z. And then what do we have? We can use the symmetric sums again from Vieta's formulas. So I'm just going to write down the formula for the power sums and that relate to Vieta's formulas. And what we get is this. So, actually, first I'm just going to define them. So S1 is going to be equal to x plus y plus z. S2 is equal to xy plus xz plus yz. And S3 is equal to xyz. So then we use power sums. So we have that P1 is equal to S1, which is equal to 3, right? And then we have P2 is equal to P1S1 minus 2S2. And so since these are both equal to 3, and P2 is equal to 3, because we are given that here, then we have S2 equals 3. We can solve this equation, right? And so now we have S1 equals 3 and S2 equals 3. So now we can find S3. So P3 is equal to 3, which is equal to P2S1 minus P1S2 plus 3S3. So this is equal to 9, and this is equal to 9. So this is equal to 0, and so S3 is equal to 1. So now we have S1, S2, and S3, and so we can write the polynomial down. So P of t is equal to t minus x, t minus y, t minus z. But it's also equal to t cubed minus 3t squared plus 3t minus 1, right? Using the symmetric sums that we solved. So what do we notice about this equation here, right? Well, this is equal to t minus 1 cubed. And so if we want to find all the solutions to this, well, there's only one solution, which is 1, 1, 1. And so we can also know that this is the only solution because based on the symmetric sums that we solved for, right? There was obviously only one solution for the pairings of symmetric sums because we solved each of them linearly, like they were all linear equations. And the symmetric sums uniquely determine the polynomial, meaning that the only other possible polynomials that could happen would be if we were to multiply this entire thing by a factor of k, but that still wouldn't change the total, the final answer. That it would just be k times t minus 1 cubed, which would still have the same solutions, right? So that's why this has to be the only solution. So then therefore the only solution is 1, 1, 1. Yeah, so that about wraps up today's video. Thank you guys for watching.